Hello, this is Mr. Ferris, and I'm going to walk you through the rest of Lesson 5.3. The worksheet we will be working through is the one we started to work through on a few days ago. This is what it should look like. It's a table from the Census at School, and we walked through the first, 8 problems there, the first 2 sets of information. And what we're going to do next is we're going to walk through what's called a tree diagram. That starts with the second page where there's a story about Roger Federer, the tennis player. And so there's some statistics on his 2011 season, as there is in any sport, of course. And a tree diagram is one of the ways that we can represent probability. We've used tables and we've used Venn diagrams, but a tree diagram is another way to represent probability problems. And it's especially good when you have maybe a first thing and a second thing, or a condition that has to happen first and then a second thing. So if we're thinking about the way this problem is set up, it's talking about a certain percent of the time he makes his first serve, and after that happens, he either wins the points or doesn't win the points for that particular game. And so we're going to set up a tree diagram where we make the first branching structure representing the first thing that was talked about, and that is whether or not he made his first serve or whether he missed his first serve. And we're told that 63% of the time he does make his first serve. So we label the branch like this. This branching is representing his first serve probabilities. And then by the complementary rule, if there's a 63% chance he made his first serve, then there's a 1 minus 63% chance, or a 37% chance that he misses his first serve. And then the second sentence says that when this first thing happens, when he makes his first serve, then there's a certain percent of the time that he makes points, that he actually gets the point for that particular game. So there's a branching then that can come off of each of these things. And this branching is what can happen next. So if you read the second sentence, when he made his first serve, so when he's on this first branch, 78% of the time he made the points. So he made the point. And this would be he missed the point. Or he did not get the point for that game. So the second thing that can happen is whether he gets points or not. Points or not. For that particular match or game, not sure what you call it when you get a round going. And therefore, this other branch will be the complementary of 78%, which would be 22%. And then again, this is whether he got the point or not for that particular round. And looking at the third sentence, when it says he missed his first serve, he only got 57% of the points. Or for 57% of the time, he won the points. So he only made the point 57% of the time when he missed his first shot. And by the complementary rule, that means that 43% of the time he must have missed his point or did not get the point. So we've labeled a scenario here where there's sort of a first thing or maybe a condition. It's whether or not he made his first serve. And then after that, it's whether or not he got the point. So now if you read the top branch, we know there's a 63% chance that he made his first serve. And of those 63% made serves, 78% of the time, he made the points. So the question would be, what's the answer to this? What percent of the time do both of these things happen? He made the first serve and he got the point. Well, if that's an and problem, if you just say it out loud, he made the first serve and he made the point, an and problem is a multiplication problem. And because this is a conditional probability, we know you would just multiply them together. So if you take 0.63 times 0.78, if both of these things have to happen, there's about a 49% chance that both of those things would happen in that order. And if you just keep multiplying across, you'll get the probabilities for all the other things that can happen. So he could also make his first shot, but not get the point. That happens 22% of the time out of the 63% of the time, which again, if you multiply, you'll get the right answer, which is almost 14% of the time. And then if you just keep going down the tree, multiplying across will give you the answer to the ands. The problems where the first thing happens and the second thing happens. First thing happens and the second thing happens. And you can get all the probabilities of all the 4 combinations of things that can happen. And of course, if this is legitimate, then this should add up to exactly 1 or 100%. Now, given that you've got the tree made, then hopefully we can answer questions about probability. For instance, what's the probability he makes his first serve and wins the point? So makes his first serve, puts him on this branch, wins the point, puts him on this branch, and we just figured out the probability is 49% roughly. So we can just read that right off of the top branch. And then the probability that he wins the point, well, winning the point is actually, there's 2 ways he can win the point. He can win the point after making his first shot, or he can win the point after missing his first shot. So there's a 49% chance of this happening. There's a 21% chance of this happening. So what's the probability that he wins the point either this way or this way? That's kind of what we're saying. He can win the point this way or he can win the point this way. And generally when you use the word or in probability, you're going to add those together. So if you do in fact add 49% and 21%, you get about 70%. There's about a 70% chance that he gets the point. You can tell now why he's a pretty good player. 70% of the time, no matter what, he wins the point. That's going to win a lot of tennis matches in the long run, of course. I will let you fill out the table. The table is just the same information, but just put in a tabular form. And so I'll let you figure out how that goes. What I would like you to do next then is to take another problem. This one is about media usage by young people. And I would like you to answer all 3 problems, which would be draw the tree diagram, find this particular probability, and then solve this given that conditional problem. So I would suggest you pause this and complete this in the space provided, just like I did, and write your 3 answers down below. If you scroll down, I am now going to do this problem about mammograms, because this is one of the more interesting things that can happen with probability. There's a surprise here at the end, and it's not just a surprise, it's actually something that is a life lesson that you should know when you're dealing with probabilities of cancer and probabilities of sicknesses and diseases that are rare. When you're dealing with those, there are some probability things that you should just know about, because sometimes doctors will tell you that you have something and it may be that there's a pretty good chance that you do not, and that's why you would want to get a second opinion. So if we would approach this from a tree diagram scenario, there's kind of a first thing and a second thing, and if you think about it, it would make sense that the first branching that you would want to do is the truth about breast cancer. And so we'll put one branch that would stand for does have cancer, and the other branch would be does not have cancer. Because that's one of the first things that they said. One of the first things that they said is that 1% of women age 40 or over, that is a certain part of the population, 1% of women age 40 or over has breast cancer. So that's a pretty small probability, and that's what makes this have a surprise at the end. When you have a very rare disease or a very low probability of something, some crazy things can happen when you calculate probabilities. So if there's a 1% chance that a woman over 40 has breast cancer, then there's a 99% chance that she does not. So let's say there's a concern that maybe she has cancer, and so they go take a test of some sort. In this case, it's a mammogram. There's lots of different tests for breast cancer, but one of them would be a mammogram. And again, you can see how this is written as a conditional. For those that actually do have breast cancer, they have been able to see and calculate from past experience that the probability of a negative mammogram, now negative in doctor speak, is actually a good thing. If your tests come back negative, that means you do not have the disease. So that's actually a good thing. So for women that actually do have breast cancer, this 1%, the probability that they get a negative result back is 3%. So this second branch is the mammogram test. And so 3% of the 1% come back with a negative. That would mean, of course, that 97% of the time the test comes back positive, which, by the way, is the correct result. These women really do have cancer. And so the 97% you would hope would be pretty high, because you want a test to show that you have cancer when you really have cancer. You want the right answer. Even if it's a bad result, you want to know the truth. And then the third statement says, for those that do not have cancer, that's the 99%, the probability of a positive mammogram, so they're now saying the probability of a positive mammogram is 6%. And of course, that's a lie. That's not true. These women do not have breast cancer, but 6% of the time they will be told that they do. And then, of course, if 6% of the time they were told that they're due, then 1 minus 6%, or 94% of the time, they're going to be told that they do not have breast cancer, which is the right answer. So it really doesn't matter what kind of test you're talking about, whether it's a test for pregnancy or a test for having the flu or strep throat. All medical tests have a certain percentage of the time that they give a false negative or a false positive. They are not correct 100% of the time. So that's why we always want to check the probabilities very carefully. So let's fill out the rest of this. As we know, to figure out the probability of each of these 4 things happening, we multiply across. So of the 1% that have cancer, 3% are going to get a negative result back, and that happens very rarely. That's a good thing, because that's the wrong answer. If you had cancer and the test said you don't really have cancer, that would be a bad thing. But it does not happen very often. That's fortunate. Those that have cancer, most of them are given the correct diagnosis, and that happens in this percent, almost 1% of people that would happen to. And then if you do 99% times 94%, you get the probability of this scenario, which would be actually a good thing. If you don't have cancer, the test should come back negative, and we want that to be a high number. And then here's one of the error times. If you don't have cancer, 6% of the people that don't have cancer are going to be told that they do, and that would be the wrong answer, of course, and it would have some devastating emotional impact if they did not get a second opinion. So now let's see if we can answer the question. The problem that was stated, or the question, is a randomly selected woman tests positive. So let's assume that you've got a woman that has tested positive. We want to find out the probability that she actually has breast cancer. So what percent of women even do test positive for breast cancer in the first place? Well, here is one and here's another. So altogether, there is, if you add these up, altogether, there's a 0.0097 plus a 0.0594. So almost a 7% chance, roughly a 7% chance, or 7% of the women actually do get a positive result. But of those that got a positive result, of the probability that you would be told you do have breast cancer, the ones that actually did have cancer, is just the 0.0097 group. That's the group that actually had the cancer out of the total that were told they had cancer. And when you calculate that probability, look what you get. You get about a 14% chance. So think about that. That means that a woman that's told that the test came back positive for breast cancer, the truth is there's only about a 14% chance that she actually does have breast cancer. So that is why we have to be very careful with a lot of diagnoses, especially for rare diseases. Rare diseases have this quirky thing that can happen with false positives, false negatives, where there's actually a very small chance that you have what they tell you that you have. So you should always get a second opinion or get another test just to be sure. Of course, with cancer, there are other ways to check, and one of the best is to get a biopsy and then have it analyzed, and then you pretty much know for sure. Now I would like to show you the solutions. This is the solution to the problem I asked you to do earlier. So if you want to give a quick look, you can see one way to do the tree, and then they give you the calculations and the final answer to part B, which is about 66% chance. And then for part C, again, they show you all the work, and the final answer is about 17%. So you can, of course, pause this if you want to get some more detail on either the work or where they labeled things. But that's the solution to the media usage problem that I assigned just a few minutes ago. Now I would like to walk through the second part, maybe it's actually the third part, of Lesson 5.3. For this, you'll need the PDF that is on the e-learning page for today. It's the Lesson 5.3b. And it's about independence of events. So this could be confusing because the word independence let me put it this way. The word independence outside of a stats classroom may mean something very different than the meaning of independence inside a stats classroom. Generally, independence, I guess, kind of means that they have nothing to do with each other. So if you are totally independent from your parents someday, I suppose that means you have nothing to do with them. They don't have any influence on you. You don't have any influence on them. And hopefully that'll never happen, that you have total independence. But you tend to get more independence as you get older and go to college and things like that. Or let's say, think about schools here, Noblesville High School, and maybe let's take, Hazeldale Elementary. Those are two schools that are pretty much independent. We really don't have any dealings with them, and they don't have any dealings with us, and eventually their kids, get to the high school. But right now, I think you could say that Hazeldale and Noblesville High School are pretty much independent of each other. But both of those examples are not what I'm talking about when we talk about independence in a stats classroom. So what are independent events? What exactly are independent events? In our world in statistics, independent events are events such that the occurrence of one event is that spelled right, or is that supposed to be an E? I don't know. Events such that the occurrence of one event does not affect and here's the most important word in the definition, does not affect the probability of the other event occurring. So, in the world of statistics, when we talk about independence, we're talking about independence of probabilities. Knowing that one thing has happened should not have any effect on the probability of something else happening. That is our definition of independence. So, if we go back up here and look at some of these examples, think about if you take a coin and you start flipping it. The probability of getting heads each time is totally independent. If you get heads on the first flip and the second flip and the third flip, that actually has nothing to do with the flip of the fourth one. Because generally speaking, if it's a fair coin, of course, there is a 50% chance of heads every single time. So just because heads has come up 3 times in a row, there would still be a 50% chance of heads coming up on the fourth time. The probability of being a male at Noblesville doesn't have anything to do with the probability of being a senior. Let's think about this. If I said, what's the probability that I would randomly pick a male at Noblesville High School, you'd probably say, it's about 50-50. About a 50% chance that you'd pick a male at random from Noblesville High School. But what if I said, wait a minute, I happen to know this person is a senior. Okay, so knowing that somebody is a senior, does that affect the probability that they are a male? Well, probably not, because I'm guessing probably about half the seniors are males too. So even if you knew that somebody was a senior, they would still have a 50% chance of being a male. That's an example of one event's occurrence not affecting the probability of the other event occurring. Now, with decks of cards, it might get just a little trickier. We want to see if picking a 5 has any effect on the probability of picking a red card. So one way to do that symbolically, we could say, all right, well, what is the probability of picking a 5 in the first place? The probability of picking a 5 out of a deck of cards, well, there's 4 5s and there's 52 cards. So there's a 4 out of 52 chance, or another way to write that, that's a 1 out of 13 chance. But what if red has already occurred? What would be the probability of getting a 5 given that red has already occurred? In other words, given that you know it's red already, what's the probability that it's a 5? Well, if you remember these given that problems, there are 26 red cards in the deck. And out of those 26 red cards, there are 2 5s. 5 of diamonds, 5 of hearts. Well, looky there. There's a 1 in 13 chance of picking a 5. There's a 1 in 13 chance of picking a 5 if you happen to know it's red. It did not change the probability of picking a 5. So the occurrence of being a red had no effect on the probability of it being a 5. This is what independent events look like. So some examples of not independent events. The probability of picking a heart when you're dealing cards out of a deck. The probability of a heart is going to change every time you get a heart. So when you're dealing cards out of a deck, the first card that comes out has about a 1 out of 4 chance of being a heart. But the second card that comes out of the deck only has a 12 out of 51 chance of being a heart. And then the third card only has an 11 out of 50 chance of being a heart. So when hearts start coming out of a deck, the probability of a heart is changing every time. There's less and less chance of it being a heart as you remove hearts out of a deck. So picking hearts out consecutively when you're dealing. Now, when you're dealing cards, generally you take them out and you don't put them back in. Then they are not independent. When you're picking an ace, the probability of getting an ace changes as you pick aces and you don't replace them back in the deck. Kind of the same thing as getting a heart. How about football player and male? That's an example from high school. What's the probability that a Noblesville High School student is a football player? Well, I don't have any idea. Let's just, for the sake of argument, say there's 100 football players out of 3,000 students. I'm just kind of rounding off to make that easy. Let's say that's the probability that you would pick a football player out of our student body, 100 out of 3,000. But what if you already knew they were male? Now what's the probability? Well, if about half of our student body are males, well then that's probably going to be out of 1,500. And out of the 1,500, you would still have 100 football players out of that. And clearly these are not the same probability. So knowing that somebody is a male does in fact change the probability that they are a football player. In fact, it makes it twice as likely. If you know somebody's a male, they are twice as likely, roughly, that they would be a football player. So these would be examples of events that are not independent because knowing that one thing happens does, in fact, change the probability of the other thing happening. So what about coin flips? If you flip a coin 5 times in a row, are those independent? And I think I already mentioned that. Yes, they are. And that's because knowing heads occurs in any flip, knowing heads occurs has no effect on the probability of future flips being heads. So we always want to talk about the probability either changing or not changing. If you roll a set of 5 dice, or the 5 dice rolls independent, say the game of Yahtzee, for instance, uses 5 dice. If you roll those 5 dice, I think generally we would say they're independent. Now, they may bump into each other a little bit, but, you know, they're kind of just randomly bumping into each other. So just because the first die is a 6 shouldn't really have any effect on the probability the second die is a 6 or any other number. So generally, dice rolls and coin flips are considered independent of each other. But we get now to number 3, and this is a problem that you'll likely see in the future when you're given a table. and you're trying to see, is there a relationship? So I guess one way to think about this, when they say, is there a relationship, that could also just kind of mean the word association. A relationship or association. It's kind of synonyms, I guess. And I hope that makes sense that if two events have an association, well, then they are not independent. These are antonyms. Being independent and having an association are the exact opposite. So sometimes they will ask the question and talk about independence, and sometimes they may ask the question and ask about association or relationship. And you just have to be careful that you know that, well, these are antonyms, and so if they are independent, then they would not have a relationship. If they do have a relationship, then they are not independent. So they want to know if there's anything going on between gender and finger length. So if you just kind of say that out loud, what does it mean to have a relationship between gender and finger length? Well, it means that if you are a particular gender, then that might affect the probability that which finger is longer. These are the finger length survey questions from Census at School. So if there is some sort of relationship, then maybe females have a higher probability of an index finger being longer, or maybe males have a higher probability of the finger length being longer. So how would you see those probabilities in a table? That's really the question. How would you see whether or not these probabilities change as you go up and down? Well, one way to do it is kind of symbolically. We did that with the card decks. We want to see if the probability of being female, for instance, I just kind of picked that randomly, is that the same or not as the probability that you're a female, given that, let's say, your index finger is longer. That would be one way we could test. Well, let's see. The probability of being a female would be 212. There's 212 females out of 452. And if we want to find out the probability of being a female, given that the index finger is longer, well, there's 123 that have a index finger that's longer. And out of those, there are 78 females. And now we just want to compare these two and see if they're equal or not. So if you calculate 212 divided by 452, you get about 47%. If you calculate 75 divided by 123, you get about 61%. And those appear to be quite different. There's a 14% difference between these. So I think it's pretty safe to say that no. Well, actually, I guess the answer is yes. The way they asked the question, is there an association, is there a relationship? Yes. We could say that given that you have an index finger the longer, there's a higher chance that you're a female, just by looking at that. So notice what we did. If you look at the table, we took the total females divided by the total students, and we got 47%, so roughly half. But then we went up here to see how the index finger would go, and we did the same calculation, but we just did it conditioned on the index finger, and we found that that was a very different percentage. And that's what you want to do to check and see if they are independent or not. If these are very different, well, then something is going on, and we would say, yeah, there's a relationship. Now, when you have multiple rows, though, you got to be careful, because it could be that the overall is 47%, and then maybe just for some reason index finger was about 47%. And you might think, oh, they're exactly the same, so they're independent. So you would probably want to make sure that you check 82 divided by 234 and 52 divided by 95, because if there's total independence here, every single one of these percentages should be about the same. We would probably give them, 1 or 2% wiggle room. But if all of these happen to be about the same percent, then we would say, well, gee, there's nothing going on. You get the same percentage of females in every single finger group. And that's what independence would look like. But clearly that's not happening here. And I'm guessing if you did 82 out of 234, that would be a much different number. And 52 out of 95, that might be a different number as well. But we just, when you're proving the negative, I guess, when you're proving an association, all you need to find is one example where the probabilities are very, very different. So you will see problems like that. Here's another one that I'm not going to do, but you can see these are the kinds of problems that you would be asked to answer. And if they're independent, then you should be able to do some calculations like this one. I'm thinking in my mind, what I'm going to do is I'm going to do vertically. I'm going to do 4 divided by 10, 4 divided by 6, 6 divided by 12, 2 divided by 10. If these are totally independent, then those should all equal whatever 16 divided by 36 equals. That's the overall percentage of females. And I can tell right now that's not gonna be independent, because 4 out of 10 is 40%, 4 out of 6 is 66%, 6 out of 12 is 50%, 2 out of 10 is 20%, and the overall is just a little under 50%. So these 5 probabilities are all going to be different and widely different. And so I guess I'll go ahead and answer it since I did it in my head. Are these independent? No. The explanation then would be to put this into words. We would say something like the percentage of females in these different groups are vastly different, and I would give a few examples just to prove that. So that's it. That's the teaching that I wanted to do so you could get some direct instruction on the last part of section 5.3. So hopefully now you've got the information you need to do your practice and then finish up with the quiz that will count for a grade.